Hello, everyone. Welcome back to our YouTube channel, Becoming a ROS Developer. My name is Rodrigo, and today we have one of our students, Johnny, who has completed the course ROS 2 Basics in 5 days. And at the end of this course, you can actually come here and present a project implemented on a real robot in order to get one of our certificates. So that's what we're going to be seeing here today. So hello, Johnny. How are you?
Hello, everybody. I'm doing all right.
All right, excited to see your presentation and your work. So whenever you want, please just share your screen and just tell us how you've accomplished your project.
Okay. I will share my screen now. Can you guys see my project all right?
Yes, I can see the robot, the terminal, and an IDE.
Great. I just finished sourcing my this my the script I just compiled. Okay, and now I'm going to start the robot, and then as the robot moves, I will talk about what it is doing. Is that all right?
Great, that's perfect. Yes, that's what I
Okay.
want.
Let me go. Mm, Follower, yeah. Launch. Okay, now I started uh, the main launch file,
Mm-hmm.
and the first thing the robot does is, as you can see here, it requests a service, which is the find wall service. It found the wall, and
Mm-hmm.
then it goes directly to the follow wall node when it starts following the wall as it's doing right now. And as you can see here, there are some messages being printed here, and those messages are being sent by another node, which is the action node that is recording the odometry, and it's recording all the points the robot is going through, and it's sending as feedback the total distance the robot has gone during the execution of the program.
Awesome. I see that you have a little controller in there too for the movement.
Yeah, yeah. When you're not using the software, you can use this controller as a
Oh no, no, I'm sorry.
uh,
I mean line
what?
116. You're controlling the angular velocity there in a, I'm assuming
Oh,
like a,
no, no. This is the PID I implemented. I talk about
right.
this in the presentation. Can I go to the presentation now?
Yeah, I mean, we are seeing it go around. So yeah, yeah. Well, yes, perfect.
Okay. Um, so I prepared this presentation mainly if I send this video to someone that has no idea what's going on. So, uh, hello everybody, I'm Johnny. The other guy explained first what's happening here, and what I'm doing is controlling this robot. It I can control the speed of the robot, both linear and angular speed, uh, through a speed controller already implemented, and I also can have access to the laser that sees the distance between the robot and 300 and 720 degrees, 720 different laser points around it. And what I did here is I need to make a service that finds the wall. I need to make a node that controls the robot, so the robot can follow the wall and go around the field. And I need to make an action server to record the odometry. And I people generally use pseudocode, but I prefer state machines. So the find wall, the find wall service, it works by receiving a request, and then the robot starts rotating, and it rotates until the laser forward, which is the laser right in front of the robot. It's between the 5% smallest uh, lasers in the whole thing. So it starts rotating, and when the laser forward is in the top 5% smallest, it means it's in front of the shortest distance to the wall, and then it goes to the wall until it's less than 30 centimeters, and then it starts doing the same thing but now the shortest laser should be the one in its right. So I know the front of the robot is pointing in the right direction it should be pointing to in order to start the to walk. And then the follow-up behavior that was proposed by the course is a simple bang bang control. So there are two main behaviors: the go away. If it's too close to the wall, it starts going away, and if it's too far, it starts going closer to the wall. And when it's uh, close to the wall in its front, because it's trying to follow the wall in its right. So when it's close to the wall in its front, there's another behavior which is the turn right behavior. And this works very well, and I think it's a very good proposition for this course because it's very simple, and it's not a control course, it's a ROS course, so I think it's very appropriate. But I the result is not as good as a PID controller, so I tried to implement a PID. I ended up implementing a PD controller because of the second behavior, the turn right. It would accumulate error in the integrator, so I would need to develop some kind of anti-wind up system, and it would make things more complicated. It's possible, but still, the PD is good enough. Where I just send a speed to the robot, so it's going forward, and the angular velocity is controlled by this PD function, and the input of the function is the error, which is the set point, which is 25 centimeters, minus the laser right, would be the measurement of the distance between the robot and the wall on its right. And here I prepared a comparison between the bang bang control and the PD controller. And at first, it's not much different, but as we can see, uh, as the trajectories overlap each other, we can see that the PD, which is the orange one, it follows the 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 bounds of the field much better than the bang bang controller. And I try to, and this is in simulation, of course. I try to do the same thing in the real robot, but unfortunately, as we all know, uh, the odometry, it drifts apart, so we don't have a very clean shape. And for some reason, the odometer of this robot has this big discontinuity in the beginning that I don't know why. And of course, the gains of the controller, I tuned the controller in the simulation. So when I go to the real robot, it's not as perfect as the simulation. I would need to tune it again. And the to record odometry, well, it's a simple action service. As soon as it receives the request, it started appending the odometry to the list that's going to be returned to the user at the end, and it starts to update the total distance that's going to be sent as feedback in the oh, this is the list that's sent at the end. And at the end, when the current place is close enough to this place it started, we assume that it has completed a whole turn around the field, and then it sends a response. But here is the simulation, and as you guys can see, it sends. I sped up the video so we can see the whole thing, and we can see that the feedback is sent, and after the feedback is sent, the robot gets close to the point of return, completed the whole turn, and here we can see the returned message. But in the real robot, we don't see it. Oh, actually, we do see it, but
Nice.
it was luck. Why I say it was luck? Because the odometry in the real robot, it drifts, right? So the real robot, it's about 5 meters, 5.3 meters, the total run. And generally when it gets to 5.3, it prints the response. But here we see that the robot had to go through more than a total turn to give us the response, because the odometer drifts, so it doesn't represent the real position of the robot, right? There's an error that was accumulated, and here we got a pleasant surprise that apparently the errors started accumulating, and after some some turns, it got the odometer got to the right place, and we got our response of all the points the robot has gone through. And that's basically it that I wanted to talk about. And I'm open to questions.
Okay, awesome. Really, really nice presentation, Jonathan. Really, really
Thank you very
clear
much.
and you demonstrated a very good understanding of the concepts that we try to teach in this course. So, congratulations. I really, really liked uh, two things: your diagrams, very clarifying on what the logic is doing, um, and also your odometry plot there was very, very nice. Can I ask, how did you
Yeah.
do that?
So I thought about using a ROS bag,
Mm-hmm.
but it was easier to just use the CSV Python, import CSV, and just and I have the CSVs here.
Uh-huh,
See,
cool.
so I just did a bunch of CSVs of the odometry in simulation, which was more straightforward than the ROS bag. Of course, if I wanted to gather information for to use in a later simulation, I would need to use a ROS bag. But I just wanted a simple script to prove that the PD is better than the bang bang,
Uh-huh.
so I used the CSV.
That's a perfect way to show it as well. So really nice. Is that just Python that you did that graph on, or
Yeah, yeah.
MATLAB? Okay.
Imported the CSV.
And
I don't
just
have it here anymore because I'm not using it. But you just import CSV, and the CSV package in Python, you can generate CSV files. And then I use
nice.
the matplotlib, of course, to make the animation.
Uh-huh. Uh-huh.
Yeah.
Very nice. Uh, so um, I was curious about the last step here about the returning of the odometry points once the action is completed. And you mentioned that the odometry drifts, and yes, it does.
Hmm.
And it also probably explains why in the real robot, you saw that kind of straight line, and then it was
Exactly.
flipped a
Yeah.
little.
There's a very strange discontinuity there.
But also, I think uh, specified the it has to be, I think, 5 centimeters from where the robot
Yeah,
started
yeah,
in order to trigger
yeah.
that condition. And I think this is a mistake on my side because it's not the point of it. So I think if you also made that bigger to 20, you would
Of course.
you would have
Yeah.
this. Yes. So I think, but this shows great of how it's if it's not you haven't told it the action hasn't completed because it hasn't arrived to that position in terms of the odometry. You can then add more things like transform frames or something with the lidar to pinpoint uh, the starting position. But this showcase is great, and I love that we still see it run around and implement that controller, and it's doing all right. Uh,
Yeah. And
maybe
you can
the
see it's a bit frustrating that like in simulation the gains I got to the PD controller made it go like in a very straight line. It's almost perfect, but in the reality
yes.
it goes all wobbly as you can see here. It goes a
Yes, and
bit
it would
crazier.
be
Yeah,
interesting to see why, and I'm assuming the frequency at which this node is spin could be maybe either too fast or too slow. Uh, but
probably. But I think the main thing is that I tuned the controller in simulation, and this is just a zero shot transference of the controller.
okay,
So this system is a very non-linear system. So very small differences in the parameters of the system would generate very different results at the end.
right, right, and the controller you have the set point is the right side of the robot, right? The right,
Yes,
and it's
exactly.
just one value.
Yes, 25 centimeters. The robot should stay 25 centimeters away from the wall in its right.
But that's one index you're looking at. Or is it like a range of indices of your LiDAR that you're inspecting and
No,
taking an
just one,
average?
just one.
Just one. Okay, that
That
might
yeah,
be
yeah,
another
and
issue. Uh,
yeah, that's an issue because when the robot moves, the angle moves, so the value changes a lot, right?
yes,
And that's part of the non-linearity of the system. We can linearize it around a very short angle, so when the angle the z angle of the robot. It's very small. We can consider it that it's approximately linear, but when it changes a lot, then the behavior is very nonlinear.
Uh,
Yeah.
I also I think there is a difference in the simulation um, versus the real robot in terms of the amount of indices of the lidar. So maybe that is introducing. I
Oh
think
yeah,
there's a
I
1080
remember
and
that. Uh,
720,
no, so in the course, the robot has 360 indices,
360.
and in the real world, the robot has 720. But I discovered that the hard way, trial and error. And
Mm-hmm.
as you can see here, in my laser callback, I have the simulation laser, and I have the
Mm-hmm.
real laser. See?
Yeah, yeah. Uh-huh.
So when I go from simulation to the real, I change the indices because they are different.
Great. Okay, so this is perfect. Really, really nice presentations, Jonathan. Again, two things I would suggest maybe to see if we can even, because that's amazing that you went a step further and implemented a PD controller. Very simple, but it shows the improvement. Two things I would try. I don't know if it's going to help, but instead of, I have a feeling it does. It will. So. Instead of checking just one value, why do I say this? Because in the real robot, especially if it's sunny or something happens, maybe one value will return an infinite. Um,
Hmm.
in fact, you see a lot of
I
that.
have a video of that, by the way.
Mm.
Uh, it's very sunny in Spain. Am I right?
Yes, very sunny.
So yeah, I sometimes when I logged into the system, there was a very bright sunspot around this region,
Uh huh.
and when the robot passed through the sunspot, all the values go to infinite.
Yes, so that's
Yeah, and the only thing I could do is wait for a cloud to go the sky and make the robot only walk when the sky is cloudy instead of sunny.
I'll figure out a way of closing that blind without making it too dark. Uh, but
I have a
yes,
video of that if you want. It's very interesting.
But yes, that I would do. Change one value to a range and then take the average or something, or take the two values as your set point. Because for example, what I do for a simple go around the wall like this, but for like another robot, I actually take two values. One that's like 45 degrees kind of up and one down. So instead of looking at only the right side, you're looking at a little bit above and a little bit below. And your set point is the difference of those to be zero, which means that this triangle between the robot and the wall has to be sort of equal, equilateral or whatever. And that way, it's another way to do it on two spots. So maybe that can also help with
I
the
didn't think about that, and it's a very good idea. Yeah, I would
especially
like to
it
implement.
also works when looking at the wall. If you do it further up, right? If you do almost in front but not quite, let's say 60 degrees, once you reach the wall, that's gonna change, right? Like the front light, the front
Yeah, it will
distance
abruptly get smaller, right?
so that will try and
Hmm.
fix. So, but I mean, again, these are just extra things on top of the extra thing you did, and I just mention it because I see your interest, and I think it's very worth it to spend the time on that. So I just want to um, finally congratulate you again, Jonathan, and yeah,
Thank you.
you've answered all my questions, and you did a stellar job here. So congratulations. All right, guys. So let me go here back to my screen. And yes, this is what you can do when you are done with our courses. You can present a real robot project on a real robot, and you can get a certificate afterwards because we want to know that you've taken something out of our courses, and our certificates really mean a lot to us. So we do require this extra step, and also helps you solidify your learning in ROS. So I want to invite everyone that is watching to do what Johnny did here, and to keep pushing your ROS learning. And that's it for us, guys, today. We'll see you guys for the next presentation. Thank you, Johnny, and we'll see you soon. All right? Bye-bye, everyone. All right, we are done.